All right, we've now moved on to regression, the last topic. So with regression, here's what I'm going to do. We tended to struggle, and I've heard a lot of comments about that. So I'm going to do a quick reteach of regression. So this video is going to be the reteach of high points of regression. And then after that, we'll do a few regression FRQs. So a study is made relating power and cold cranking amps of auto batteries as a function of price. Data from a random sample of batteries generates the following computer output. Right? Write the equation of the fitted regression line. Define any variables used in this equation. So first off, the most important line is this constant line because that tells me where my y-intercept is. And what's below it tells me that's my slope. So this is my y-intercept row. Everything on this has to do with y-intercept. Everything on this has to do with slope. The price is my x value. And when I read this thing, I really can't even tell which it is. So, but it says as a function of price, so f of x. So they're saying, but this is cold cranking amp, so this is my y. So the very first thing says, okay, write it that way. So I could have put cold cranking amps equals, see if I can get this all on the page. Yeah, it looks like I can. My y-intercept right here, 410.597 plus 0.552957. Now, if I write it like this, I have to define my variables. Y is battery power in amps. X is the price of the battery. But if I write it like this, making sure to keep the y hat on, then I actually have defined it, and I could write it just like this, and that would be a full credit response just like that. Okay? Identify and define the meaning of the slope in the context of this problem. Well, my slope, we already know that that's my slope. And I always say, which is right here, I always say put it over 1. So in this case, I would say 5.529 over 1 and label it. And this is wrong, and that's wrong. This is amps, and this is price. For every one, so this is wrong. For every $1 increase in price, there is an expected 5.53 amp increase. All right. Remember, price is my X. So for every $1 unit, every $1 increase in price, or 1 unit increase in price, there's a 5.53 increase in amps. Sorry about that. Using the computer printout, calculate, interpret the standard deviation of the residuals in the context of the study. I'm not going to ask you to do that at this point. I'm just going to ask you to find it. And it's going to be labeled by S. So my S is 74.29. The standard deviations of the residuals is 7.429 and gives us the amount of variation we can expect in amps from the regression line for a given amount of price, or for a given price. Looks like I have my X's and Y's swapped all the way through, so this is going to be fun. Identify and interpret the value of the coefficient of determination in the context of this problem. Well, usually they will give us two. They'll give us the R squared adjusted, which we'll not use, and we'll use this. All right. So 68.3% is it. The variation in amps can be explained by changes in the price of the battery. Calculate and interpret the correlation coefficient in the context of the scenario. Well, I need to know the sign of the slope. Well, the sign of the slope is positive, and then I just need to take the square root of the R squared. So The correlation coefficient is 82.64. There's a strong, important word, positive linear relationship between battery price and battery power, all right, or battery price and amps. These can swap places and it won't matter. Please remember, if it's 0.40 to 0.75, it's moderate. Less than 0.40 is weak. Greater than 0.75 is strong. But you must have the level of strength, you must have the direction, and you must have the word linear because you're telling us what type of relationship it is. Identify and interpret the standard error of the slope in the context of this study. Well, so that tells me that I am looking on the slope road because I'm looking for something that deals with slope. And sometimes this will say standard deviation, sometimes it'll say standard error, but it's the next thing next to the slope. So this is my standard error. And the standard error of slope is 1.135. Because the slope is estimated from a sample, other samples are likely to have differing slopes. The standard error slope quantifies the amount of variation that we could expect from different samples. This is just a sentence that you got to memorize. All right. There is a linear relationship. Oh, so is there statistically convincing evidence that there exists a linear relationship between the response and explanatory variable? Assume all conditions have been satisfied. So with that said, we always start off with the equal because we always start off with the positive. Well, and here it'll be not equal. If it equals 0, there is not a linear relationship. So be careful because it's a horizontal line. All right. On this case, it's saying, oh, it's not a horizontal line. So there is. Beta 1 is the true population slope for the relationship between battery price and power. Conditions were met. I need to show you how to get the T. The T statistic comes from right here with 5.529. If I divide that by 1.135, I will get 4.87. So that gives me that p-value of 0.005, which they give right here. Or they were supposed to. Not sure what happened. So we reject. There is sufficient evidence at alpha equal to 0.05 to suggest that there is a linear relationship. Well, this should be about 0. There is a linear relationship between battery price and battery power. Okay, so the slope of the line is not 0. Because we rejected the null, we rejected that there's not a linear relationship, but we believe that there is a linear relationship. Please remember, equal 0 means not a linear, does not equal 0 is a linear. I know that's backwards, that's twisted from what we've done everywhere else. Be careful with that. Create a 93% confidence interval for the slope of the least squares regression lines, assume all conditions have been met. Well, you need to know that slope, this formula is slope plus or minus T star times SE of the slope. So our slope is this, so we write that down. Our SE is that. This is a T statistic. It's not T star. You can't use that here. So slope, there's a SE, but I need to calculate this T star. Well, I need to know how many degrees of freedom they have. Well, right here I have 11. So that tells me my degrees of freedom is 11, and my sample size happens to be 13 because degrees of freedom is n minus 2. So in this case, my sample size must have been 13, but my degrees of freedom comes right there from the residual is 11. So second quit. second vars, inverse t, parenthesis 1 minus 0.93, close parenthesis, divided by 2, degrees of freedom, 11, and I get the 2.066 that I have. So we are 93% confident that the true population slope for the relationship between battery power and price lies within this interval. And you're probably going, well, how did you get that? And the answer is I had to calculate it by hand. I had to go 5.5 plus 2 times this, and then 5.5 minus 2 times that. And if I did that, I got this value. Now, something I should notice there is 0 is not included. The fact that 0 is not included tells me that I have a statistically significant slope. All right? Tells me my slope, if 0 is included, can't say it's statistically significant. But if it's not included, it is statistically significant. All right, the next part of this is we're going to do some multiple choice to try to help some of this out. As a part of a class project at a large university, Amber selected a random sample of 12 students in her major field of study. All students in the sample were asked to report their number of hours. Amber wants to compute a 95% confidence interval for the slope of the line. All right. Which of the following gives the margin of error? Well, please remember, let's work with the formula for slope, for the confidence interval. Slope plus or minus T star SE of slope. Well, that right there is my margin of error. Well, SE of the slope comes from right here, and that's 0.0745. I need T star. That's not that value. So I'm going to have to go to calculate it. Second vars, inverse T, parenthesis, 1 minus. What is this? What type of confidence interval? 95%. 1 minus 0.95, close parenthesis, divided by 2. My sample size is 12. So my degrees of freedom are 12 minus 2. My degrees of freedom are 10. And I end up getting 2.228. All right, that takes care of that one. A least squared regression line was fitted to the weights in pounds. All right, the equation is this. Which of the following is the residual in pounds for this child? All right. The actual baby weighed 25 pounds. Okay, so residual equals observed minus expected. Well, we observed 25. All right. Well, we have a 20-month-old child, so I'm going to plug that in for the age. But when I calculate that, I get 29.6. So 25 minus 29.6 is a negative 4.6. So my answer choice is B. Be careful. Pay attention to that, because remember, it's observed minus expected. In this case, my observed was less than what I expected. My observed was less than what I expected. I expected 29.6, but I only had 25. The weight in pounds of a full backpack and the corresponding number of books in the backpack were recorded for each of 10 college students. Resulting data were used to create a residual plot and the regression output below. So here's our residual plot. And notice we're centered on 0, and it looks pretty random, and that's good. So it says, which of the following is closest to the actual weight in pounds of the backpack for a student who had 4 books? All right. So there's my slope, there's my y-intercept. So there's my equation. Y equals 10.53 plus my slope times x. Well, x happens to be the 4, so I'm going to plug that in. But when I do that, I find out that I'm predicting a 12.65. Well, remember, residual equals observed minus expected. Well, we just said we expect 12.65. And we want to know the observed, that's what we don't know. But we can come up and estimate our residual. We can go up to the point right here and over. And I'm going to guess this is about 2.25, call it 2.3. If I add that to the other side, I end up getting 15.95 equals 0. Excuse me, 14.95. I can't add. 14.95. Well, 14.85, 14.95, and the one that's closest is 15. Once again, I added 12.65 to this residual of 2.3 because this value right here is about 2.3, and it's positive because we're above the line. All right, we're above the line. I think this is the last of the multiple choice. It is. So a statistics teacher wants to determine whether there's a linear relationship between high school students' heights in inches and their lengths of their feet in centimeters. The teacher obtains height and foot length measurements for a random sample of 23 students. All right. Which of the following and generates the following output. Now I look at that and go, gosh, that's pretty linear. Provided that the assumptions for regression are satisfied, which of the following provides a 95% confidence interval for the estimate of the slope of the population? Well, remember, slope plus or minus T star SE of slope. My slope is 0.583. My SE is 0.13, 0.138, I should say. This is not T star. I have to go calculate T star. Well, what was my class size? It was 23, because that's going to be important. So, second vars, inverse T, 1 minus 0.95, and my degrees of freedom are 23 minus 2 for regression. So 2.079. .583, 138, so it has to be, can't be these three. 2.079, it's B. All right, so the next videos will be actually working some FRQs from regression. Trying to shut this thing down.